Okay, so we're going to take a look at the 2014 P ICE paper, and we're going to look specifically at the theoretical section at the end that we can do without the practical. So we are essentially going to use a pendulum, but we're going to make it move in circular motion, so it's something called a conical pendulum, and the radius we're going to make it move in is 0.125 meters. And what you can do is measure the time period for the rotation, and essentially what we're going to do is we're going to change the length but keep the radius the same. So first thing we're going to do is complete the table. We're just doing a few calculations. So for the L squared minus R squared, both of these values should be to 3 significant figures because the data is to 3 significant figures. And then our T squared should also be 3 significant figures because the time period is 3 significant figures. So that's fairly straightforward. So what we're going to do is we're going to plot these onto a graph, and we want to find the gradient of the straight line of best fit. So here's the graph. We can stick the values that we've just calculated in. Draw a line of best fit. So we've got roughly equal numbers of points above and below the line. And going to measure the gradient of the graph from this point here. So I'm going to use 0, 0 as one of the coordinates. This would be the other coordinate I would use. And then what we can do is use that to calculate the gradient of the graph. So that's fairly straightforward. Okay, so now we're going to start putting this to use. So use your answer to part 2C to determine the time for the pendulum when L equals 0.50. So the first thing we're going to do is calculate what L squared minus R squared is, and then T squared would be that times the gradient. So if we want just T, we have to square root it, which gives us 1.40 seconds. So the relationship between T and L is given by this equation here, where G is acceleration due to gravity. Use your answer to part 2C to find the value for the acceleration. So the gradient is going to be equal to 4 pi squared over g. So then we just need to, we want to calculate g, so 4 pi squared divided by the gradient gives us g equals 9.72 meters per second squared, which you can see is pretty close to the 9.81 that we'd expect to find. Okay, so referring to the graph, explain whether or not you think this is a reliable answer. So if you look at the graph, all of the points are very close to the line of best fit. So that all of the points are giving a very similar value of g, so I would describe that as reliable. Discuss with reference to the measurement of t whether a smaller uncertainty in the value of g would be obtained if the experiment were to be carried out with a pendulum of the same length and a smaller radius. So from the experiment, we've seen L squared minus R squared square rooted is directly proportional to T squared. So a smaller radius would give a larger time period, which would have a smaller percentage uncertainty, reducing the percentage uncertainty and therefore the uncertainty in G. Okay, so moving on to some more theory based on what we've just done. We've got a circular motion being used for a fairground ride, and this one's called a chairoplane. So what you can see is we've got some people on this ride, but we've also got some empty chairs. So explain why the empty chairs are swinging outwards at the same angle as the chairs with riders. So the first thing I'm going to do is I'm going to make theta the angle of the chain to the vertical. So if we look in the vertical direction, we know the tension in the chain times by cosine of that angle should be equal to the weight force of the rider, so they're in vertical equilibrium. We also know that the horizontal force should be equal to the centripetal force. So that's what I've done there. I've divided the t sine theta by d cosine theta to get tan theta, and you can see you end up with an expression for the angle which is independent of mass, which is why they're at the same angle. Okay. So outline the measurements you would make to determine the speed of a rider around a circle under normal operating conditions. So the first thing I'm going to do is measure the radius. So I just get a tape measure or something like that to measure the radius of the circle, and then multiply that by 2 pi to get the distance traveled. Then I'm going to place a fiducial marker and measure the time taken for the ride to complete 10 full rotations. And using those two things, I can calculate the speed of the rider. Okay, so suggest a safety test to check the strength of the chains supporting a newly fitted chair before a rider is allowed to ride on it. The test is carried out when the ride is stationary. You may assume that the maximum angular speed of the ride is known. So the first thing I do is I would calculate what the maximum tension the chain is going to have to experience in the ride is, using the maximum speed and the maximum mass of a person we would allow to ride it and the radius of the ride. So once you've got that, while it's stationary, I would apply a mass with weight force about 5 times that value. And we want to make sure the chains don't break. And the reason I'm saying it 5 times is because we want to be especially sure, even when the chain gets old, that it still works. So we've allowed a lot of leeway there. And then, so that's the test that I would do. So final question, we've got a turntable to investigate friction between a wooden disc and the surface of a turntable. The turntable is flat, horizontal, and rotates with a known constant angular speed. The purpose of the investigation is to find out how the maximum frictional force varies with the weight of the disc on the turntable. So the maximum friction is the same at all points on the turntable for a particular disc weight. Okay, so what we're going to do is essentially use the centripetal force to figure out what maximum friction is in each case and see how that changes with weight. So the first thing I would do is I'd stick a fixed mass onto the disc, and we want to measure the total mass of both the disc and the fixed mass. Then what I would do is I would move the disc further and further out, increasing the radius until it just starts to slip. Because at that point, we know the centripetal force is equal to the maximum frictional force. At all the radii before that, the centripetal force would have been equal to a frictional force lower than the maximum. And then once you've done that, I would repeat that process with 6 more fixed masses. So we're changing the weight of the disc. And for each of them, calculate what the centripetal force is when it just starts to slip, which is the max frictional force. Then all I'd do is I'd plot a graph of that force against the weight force by doing m times g, and that would show us the relationship between weight force and the max frictional force. And that completes this video going through this section of the ISA.